Okay, Wino Stew students, let's go ahead and go through these answers here. This will give you a chance to self-grade and give you some idea of how you did, and also kind of understand your mistakes if you made any. And I'll get these graded as soon as I can, and you can then see that on this scorecard. Anyways, let me begin. First ones have to do with oscillations here. It says, but a mass from a spring is seen to bob up and down over a distance of 10 centimeters. So if this is the equilibrium, it would be going up and then down and then up and then down. And so if this total is 10 centimeters from top to bottom, and then twice each second, so its frequency is 2, what is its amplitude? All right, so we don't need the frequency here, but its amplitude then would be half of that, so it would be 5. So the amplitude is from equilibrium to the highest or equilibrium to the lowest point. If the mass on the end of a spring takes 3 seconds to complete one cycle, what is its frequency? And so the frequency is the reciprocal of the period, and the period is the time for one cycle. So it looks like it would be 1/3. Answer D. Number 3, changing which of the following affects the period of the pendulum. And so the pendulum, we had a period is 2 pi times the square root of L over G. And so let's see, I guess really changing the length, I guess you might say changing the planet you're on would do it too. But of the options here, mass, amplitude, angle, and length, it looks like length is our best option for number 3 there. Okay, so number 4, a pendulum is allowed to swing through one cycle and its period is measured. It is now restarted with twice the amplitude. What is its new period? Okay, so the period of a pendulum was its mass over the spring constant. So in other words, the period depended upon its mass and its spring constant, the stiffness of the spring, but never did it depend upon the amplitude. So change the amplitude, it's kind of irrelevant. So I guess it's going to be staying the same. What type of waves are longitudinal? Now, probably the first one just stands out here, sound waves. We talked a little bit about light waves, but and water waves as they were transverse. Matter waves we didn't really even talk about, but given that we talked to these 3, it's the best answer here is sound waves. Number 6. Which of the following affects the speed? And so we have this equation, and if we're not careful, we might think wavelength and frequency have an effect, which would make us, I guess, go to all of these. But hopefully what you got out of the lab, when you doubled the frequency, you noticed that the wavelength was cut in half. And so therefore the speed came out to be the same. And so these two played off each other. So it didn't change with wavelength or with frequency. Now, temperature we did talk about. That's the motion of the molecules, and that's a definite one. And so I'll say temperature. And there's, I guess, page 2. Okay. On to page 3, question 7. It says, increasing the amplitude of the sound wave would increase its, and that was how loud it was, its volume, if you will. We talked about how sound waves, our ears can detect the amplitude, which gets interpreted as loudness, and frequency, which gets interpreted as pitch. Of course, then as we talked about in the last problem, you could kind of argue wavelength is pitch too, because changing one changes the other. But anyways, the loudness A would be the correct answer. Number 8, the length of a guitar string's fundamental wavelength is, and so if you kind of remember those pictures we drew of our standing wave, the fundamental one was what I called the boring one in the sense that when I was demonstrating it, it was so slow. but also it was kind of boring because you can't see one whole wavelength. Whereas the second one, it is, the second harmonic is one whole wavelength. Anyways, wavelength of the fundamental one would look like that. And so the wavelength would be twice as big as the length of the string. And so where it says here, number 8, longer than the string, I guess would be correct. Twice as long would be even a better way to have an answer. But given these of our answers, it's longer than. So non-numerical answer. All right, on to number 9. It says the law of reflection says, and this says the angle coming in, the incident angle, equals the reflection angle. And it looks like the third one, C, is listing that best. They say the reflection angle is equal to the incident angle. 10 is our flat mirror. It says which letter corresponds to the location of the image of O. So O being our object. And we said that the image would be just as far into the mirror. And so D is our best bet. Now, this might actually be a little hard because I drew a line down here, but the mirror doesn't go all the way down there. But that's okay because the light would bounce off here, and that's part of the mirror, and go there. So you don't have to have part of the mirror straight across from the object. You just have to have part of the mirror where the, light would be reflecting off. So this person of A would trace back with their binocular vision and get point A, point D. And so, and I put A here, but I guess I shouldn't say the person has to be at A. The person could be here, and as long as it bounces off and does something like that, or the person could be here and bounces off. Now, the interesting one is if the person's here, the light wouldn't be able to bounce because you don't have a mirror right here. But we still would say the image is there. We would just say we can't see the image because you got to look through the mirror to see it. Anyways, I better move on here. Number 11 says, if the rays of light parallel to the optical axis are incident on A, and so it looks like a something mirror. So we'll probably have a flat mirror, a concave mirror, a convex mirror. Oh, and a diffuse mirror. Okay. They converge to a point after leaving. That was the property of the concave mirror. And so we said if you have some rays, and I'll just draw 3 of them, and they come in and they hit a mirror that is curved this way, which we call concave, the normal would be to the center of the circle, so I'll call it the radius of this piece of the mirror, and then half that distance is the focal length, and that's where the light would go, so that the angle of incidence equals angle of reflection. Same thing here, it would go through that magical point. Anyway, so concave is the one that focused the light. The convex one made the light spread out. All right, number 12, the image formed in a bathroom mirror is. And so let me take that as a flat mirror. We talked about flat mirrors, and flat mirrors, we always made a virtual image because they were inside of the mirror. They were always the same size, they were always upright, and they were always the same distance in the mirror that the object was in front of the mirror. And because of that, I guess A would fit those 4, well, 2 of those 4 categories I mentioned, that it's upright and it's virtual. Okay. Moving on to number 13 here. How many joules are equivalent to 21 calories? And I'll even note that this calories is a lowercase c. And let's see, we learned that there was 4.186 joules in 1 calorie. So maybe we'll start with calories and then do a unit conversion. And so this really takes us back all the way to chapter 1, where I'd say, okay, I want to get rid of calories, so I'll put it at the bottom, and I want to convert it to joules. So I'll put that on the top. So then calories will cancel off and joules will remain on top. But of course, when you multiply, you can't just randomly multiply something by a number and expect it to be the same. But if that number is a 1, it is. And so you just got to have to make sure what's on the top is the same on the bottom. And 4.186 joules is the same as 1 calorie. And so what's on the top is the same as the bottom. And we would get, a little calculator here. Let's go 21 times 4.186. And so we're looking at about 87.9, which is really close to the 88. So D, I guess, would be the correct one there. 14, why does the coldest part of winter occur during, say, January and February, when the shortest day of the year is near December? This is a little tougher one, I think. This is tied to that specific heat. I guess it would be a little bit like saying, let's see, cold. Maybe I'll put something in the refrigerator. And so if I have some piece of food here, I'll just make a little loop here. It's my leftover chicken, and so it's nice and warm, and I ate half of it, whatnot, and I go ahead and I put it in a box, actually maybe about an ice chest, and then I put ice in it. And what's going to happen is first the air or the around it is going to cool down, and it will be a little bit of a lag time before the piece of chicken gets a chance to cool down. And so that's what happens to our weather, if you will. We get less and less sunshine, and by December 21, our winter solstice, we have the least amount of a sunshine. And so that was kind of my idea of the process around it. But the Earth is going to then take a while to cool down. It won't be that cold. There is a specific heat associated with it, or a heat capacity associated with it. And so it's gonna take a while. Okay? And sometimes we refer to that as, a lag in it. The same thing, by the way, happens in summer. It's usually hottest in, July and August. In our areas, it's often August and September. But yet the longest day occurs at June. June 20, well, it can vary, 20, 21, 22. But that would be our summer solstice. Anyways, all of that I think is best explained here with D. It takes the release of a lot of thermal energy from the ground before it actually cools off. And so it's got that stored energy, that specific heat, if you will. So good for you if you got that one right. That could be a tough one. The latent heat of melting of water takes 334 kilojoules to melt 1 kilogram. How much energy would it take to melt 3 kilograms of ice? And notice we're just melting it. We're changing it from 0 degrees Celsius in ice to 0 degrees of water. So there is no MC delta T. There is no warming it up. And so all we're doing is melting it. So it would be the 334 for each kilogram, which looks like a hair over 1,000 in units of kilojoules. And so it'd be about 1,000 kilojoules. All right, on here to number 16, and the last of the multiple choice here. In conduction, thermal energy is transported by, that process was one atom colliding into another. And if the material moved, that was the convex, and so the movement of the fluid. The material moved. In fact, if it moved, it has to be a fluid. So it has to be a gas or a liquid. A solid particles couldn't move. And the electromagnetic fields would be the radiation one we didn't get a chance to talk too much about. All right, so there's the multiple choice. Hopefully that went well for you. Now let's look at the problems and get my calculator all handy here and ready to do some calculations. It says a student with a mass of, so it gives it the mass, is swinging from a rope that has a length of, what is the frequency? Well, we wrote this earlier with the multiple choice, that there would be a calculation here for the period. So let me do a quick calculation for the period and see what I get. And so 1.55 divided by 9.8 is that ratio. Taking the square root of that, multiplying it by a 2, and also multiplying by a pi, gives me a period of about 2.5. And the second half of this, since it says the frequency, would be to take it reciprocal, so 0.4. And the units for period would then be in seconds, and for frequency would be the inverse of seconds, which is a hertz. So 0.4 hertz would be the answer here. Okay. 18, it says, you observe that 22 crests of water pass you each minute. I guess I'd call that a frequency because it's how many? It's 22 every 60 seconds. I'll hold off on calculating that. Let's keep going. If the distance between the crests, so from a crest to a crest, that is a wavelength. What is the speed? So the speed is wavelength times frequency. So they straight up gave me the wavelength. Although they didn't say the word wavelength, they make you kind of use your knowledge that when they mean from crest to crest, they are defining the wavelength, or they're using the definition of wavelength to give you that. So there's the wavelength. Now the frequency then, let me do that, 22 divided by 60 seconds, that would be 0.367 hertz, or per second, so 0.367 per second. So that once I multiply them, I will get meters per second. So let me take that answer and multiply it by the 4.5, and it looks like I get a 1.65 meters per second. Okay, nice. 19, how much time does it take for sound to travel the 4,300 kilometers from the west coast to the east coast? Okay, so I'll just say distance equals velocity times time. And that goes way back to chapter 2. But now, since it talks about sound, and they don't give me any kind of temperature, so our default is to use 344 meters per second, which is room temperature, okay? And then they're, of course, asking us for how much time, so I'm trying to solve for t. And they give me the distance. We got to be a little careful with the units. This is 4,300 kilometers, so let me change kilometers into meters by putting another 1,000 there. And then meters will cancel off. And so when I move the S to the other side, I'll get this many seconds. So it'd be 4,300 and then 000 divided by 344. And so we're looking at about 12,500 seconds. Nice. Maybe I should have boxed this one too. All right, so there's the first three. And I believe we have 8. So 1, 2, 3, 4. Yeah, 5 more here. Okay. How long is an open organ pipe with a fundamental frequency? So open, it meant open on both ends. And so this side is an antinode, and this side is an antinode. And that's where we had like all these different patterns. The simplest one was when the length of this was from one antinode to the next. Now another one was one harmonic higher, and so there was an antinode in the middle, but we always had to end at an antinode for the open pieces. So since they say fundamental, I'm going to look at this one, and so I'm saying the L is half the length of the, half a wavelength. Half a wavelength is the length of the pipe. That's what I'm trying to say. So I'm trying to, find this. How long is it? I'm trying to find L, which I can do if I get the wavelength, and I got the frequency. So I think what I can do is something like this. I can get that wavelength by kind of implying that we're talking about, listening to a pipe organ. I'll say probably, inside. I know there are pipe organs outside and outside theaters. But even then, I'll say it's probably somewhere around near room temperature. That's our default if we don't know anything else. So I'll take the speed and then take the frequency. And from that, we'll get the wavelength. So 344 divided by 400 gives me a wavelength of about 0.86 meters. So then the length of the pipe is half that. So divide by 2, and we're looking at 0.43 meters. Yay. So kind of 2 steps, kind of, I guess, a little bit like, what was the other one? This one here had the 2 steps where I got to kind of figure out the frequency and the wavelength and then use that to get the velocity. In fact, maybe I'll do a circle kind of around step 1 and then a little box around the final answer. So some of these have like a 2-parter. This is a good one with that. Here's another one. How far in meters does light travel in one day? I guess I'd put that kind of in the same category as problem 19, where distance and velocity and time are, coupled together back in chapter 2. In 19, though, we were talking about sound waves. This one changes because we're talking about light waves. And we're also solving for distance instead of solving for time. So I'll put in the velocity, 3 times 10 to the 8th meters per second. And the time of one day, well, let me do this. Let me go, it's 24 hours, make a day. But then 60 minutes are in an hour. And then 60 seconds are in a minute. So that I can take this one day, right here I convert it to hours. Hours now is converted to minutes. Minutes is now converted into seconds. And then seconds is what I need to cancel off so that I can get a final answer in the units of meters. So 3 times 10 to the 8th for the speed, 24, 60, and another 60. So this is a long distance, at least in terms of the size of the Earth. So in one day, it seems like it travels really far. I think that's why most people would say light travels really, really fast. I mean, it can go all the way around the circumference of the Earth 7.5 times in 1 second. But it takes, what, 100,000 years just to go across our Milky Way galaxy. So on that kind of thinking, you would say light is not fast, light's slow, pathetically slow. It takes millions of years to get to some of these galaxies we can see with our telescope, and that's slow. Anyways, I digress a little bit here. All right, let's go to, it looks like our mirrors here. It says, if an object is placed 35 centimeters from a concave mirror with a focal length of 25, where is the image? This is a real good one. Maybe I'll do a little bit of lecture review here. Because first of all, it says concave. So I'm going to make a concave mirror. And I'm going to put a focal point right here because they say the focal length is 25. And notice they put the object further out. And so if I was drawing the rays, it would hit here and bounce off and go like that. Let's see, the radius of curvature probably would be right here. Maybe I should put a little F and an R like I did in class, because we know it's twice as far, so it'd be 50, and our object is closer than that. And so this is what we called scenario number 2, where the image here is upside down and bigger than the object. And we worked out these equations. So I hope during the exam you just use the equations we did in terms of the geometry. But I'm going to just kind of go through those again and kind of draw. I think in class I did green and blue or something. I already drew this in blue, so I guess blue's out of the question. But I'll do 2 similar triangles in green, noting that this is the height of the image and this is the height of the object, whereas this here being the distance of the object and here being the distance of the image. And of course, here's the focal length. And maybe I should write it in green, but if I set up these similar triangles, I would have height of the image is to the height of the object here, as this distance, which is focal length, is to this distance, which is object distance minus focal length. And the other set of triangles, which I'll switch over to red since I already did blue, would be this set, where we would argue that the height of the object straight across here, so height of object, and here is height of image, we would say something like this. Our similar triangles, not congruent. Our 2 similar triangles would be height of the image is to the height of the object as this distance, which we would write as image distance over focal length, as this distance, which is focal length. So step 1 in this is, again, not to do all of this geometry again. This is why I told you write these on your formula sheet and make yourself a little note. You hopefully have there these 2 formulas that say they are valid if you have a concave mirror. Okay, good, we do. And they're valid if the object distance is greater than the focal length, which is what we do, or do have. So hopefully you started this problem straight with these 2 sets of equations, because we are going to have to do image distance, which means we have to get this ratio, and to do that we have to do this step up here. So if I take the focal length of 25 and I divide that by the 35 minus the 25, then I get 25 over 10, which is 2.5. So this ratio, which is the magnification, is 2.5. I can use that right here. And so I'll just go 2.5 for this ratio. And then I will have image distance, which I want to solve for, over the focal length, which is 25, divided by 25. And so if I bring this 25 over to there, let's see, times 2 is 50, and then another 12 and a half. So that would be 62.5 image distance minus 25. And now, to finish the problem, I'll bring the 25 over. So let's see, the 2 and the 5 is going to make a 7, and the 6 and the 2 make an 8. And so, like I said, hopefully you did this a little bit faster than I just did because you started with these equations. But now, do the first one, use that result into the second one to find out what the image distance is. And in fact, let's see, the image distance was 35. Yeah, just gonna kind of checking my math here in my head. Right, so I like that. Two more here. The shortest wavelength that humans can see is violet, which is near 400 nanometers. What is the frequency? All right. Well, we did this one in class, and in fact, this looks a lot like a lot of the waves we did, where velocity, frequency, and wavelength are related. And here it was with sound waves earlier on, too. But now we're doing this for light waves, and so you would have the velocity divided by its wavelength, and the general symbol for the velocity of light waves is c, and is the 3 times 10 to the 8th. And in this case, 400 and the nanometers is 10 to the minus 9. So grabbing a calculator here, 3 times 10 to the 8th, divided by 400 times 10 to the negative 9, gives me 7.5 or 750 terahertz, as we talked about in class. So hopefully just repeat that same calculation we did in class. All right, and then finally the last one, looks like it's on the thermal part here. How much energy does it take to warm up? And we have a certain amount of ice that, okay, good, it looks like kind of like the one we did in class. The ice is less than 0, so it's got to warm up the ice, then melt the ice, and then warm up that water, and they give me the latent heat of fusion. Hopefully you remember that the specific heat is 1 calorie per gram. That's the definition of a calorie, so it's not given. It's kind of hopefully expected. So the Q, and I'll say total then, is 1 plus 2 plus 3. That is, there's an MC delta T to warm up the ice, and then there's an M L sub F to melt the ice, and then there's an additional MC delta T. Now that we've melted the ice and it's water, we got to warm up the water to 37 degrees. And the mass won't change, and so we start with this much and in ice, and it just melts, and it's always going to be 112. Now, we might have to remember that the specific heat of ice is a half, or look it up there in the table. The delta T, the temperature, would be 12 to warm it up to 0. Then we got to melt it, and so that's 112 grams, and each gram takes 80 calories. Then we have the 112 times the 1, Then we warm it up 37. And I suppose I should have put grams in degrees Celsius so that grams cancels degrees Celsius. And so this term right here is going to be so many calories. And same thing here. This would be grams and this would be calories per gram. So again, we will have plus so many calories. And then finally, these units would be the same as here. A gram, this would be a calorie. Per gram per degree Celsius, because this is degrees Celsius, so that grams cancel, degrees Celsius cancels, and we would be then with calories. And then ultimately, I can add them all together if I can just squeeze it on here as calories. Okay, so this first calculation right here would be 112 times a half times warming it up 12. So that'll be 672 calories. And this one would be 112 times 80, which would be 8,960 calories. And then this one would be 112 times 1 times 37, which makes 4,144. And so like we talked about in class, not a surprise that most of the energy is melting the ice, and the 37 would be like body temperature. This would kind of be like eating 112 grams or 112 milliliters of ice, and as you ingest the cold ice, your body's going to warm it up, then your body's going to melt it, then your body's going to warm it up to room temperature, and this is how many calories you would be using to warm up that ice. Pretty good way to lose weight. You're going to be burning some calories, but not intaking some calories. All right, so then we can add them all together, and on my calculator, I'll just do kind of a copy and paste. I forgot to put plus there. Try that again. So the first one plus the second one plus the third one. And all three together come out to be 13,776 calories. And so there's the last one. And a pretty long one there too. I don't know about the hardest one. Maybe the mirror is the hardest one. It's the one we saw the soonest. But I did give you the formula, so maybe that one is the hardest. All right, well, hope you did well, and that's a wrap for the solutions. Take care.